So we divide it by the smallest. So we're dividing them both by 0.08125, and we see it's roughly a 1-to-1 ratio. So that means we have Mg1 and O1. Now, of course, we're not going to write the ones because we're doing chemistry. So we just write down that we found MgO. If I remember rightly, a lot of you guys actually found that it was Mg2O because there was a problem at the moment because not all the magnesium reacted. Magnesium on the outside reacted, and once it reacted with a layer of magnesium oxide, the magnesium in the middle react. The reaction didn't go to reaction, so that was an experiment. How could we improve that? Well, there were ways we could magnesium lots of times, or we could make the reaction go further, or we could clean the magnesium before, because some magnesium oxide already on the outside. Magnesium does react really, really slowly. It does react with air. There were quite a few errors that could have been there. So that was your and how you calculate. I will be giving you this if they okay. On a law of constant mass to a closed system and a non-enclosed system. All right. Conservation is just that you can't create or destroy matter. Let's write that down. Law of conservation of mass is that you cannot create or destroy matter. Okay. Means that the mass of the reactants has to also be the mass of the product. So let's look at a sample equation. Let's make this one up. So I've got, I want something that's going to give off a gas. I know. Hydrogen peroxide takes water and oxygen. We also need to balance this equation. Now we think it looks balanced because we've got 2 hydrogens. Oh, oxygens are out. Oh, that's just mean. So we're going to get an even number of oxygens first. We'll go for 2 of those. And then I need to up my hydrogens. So let's, I now have 4 hydrogens on each side, and I've got 4 oxygens here, and 1, 2, 3, 4 here. If it took you a bit longer because you paused the video and you did it with dots or did it yourself, that's fine. I know this equation. Okay, I'm the science teacher. I'm supposed to be a little bit faster. So we have got hydrogen peroxide, which is aqueous. Aqueous just means it's in water. We've got water, which is a liquid. It's one of the few liquids. That's an L, by the way, not an I or a 1. Okay, so let's make it into an L. Let's give it a little bottom. And we have got oxygen, which is, of course, a gas. Okay, we can't create or destroy matter. If we were to do this in a closed system, we put it in a box, yeah? We put peroxide on top of the weighing. So here's the weighing scale there. It tells me what the mass is, and it's inside a sealed box. Okay? Nothing can get in or out. A little beaker there with my hydrogen peroxide in there. And it gives off lots of bubbles because it's giving off oxygen. I'll probably put a catalyst in there as well because I don't want to for a week. And that mass doesn't change. I create or destroy matter because I can't. Okay, that's the law of mass. And the gas given off, the oxygen here, contained in the box. Okay, now imagine I did this in a non-closed system. Okay, another scale here. I'm going to measure my mass. I've got my beaker here. Okay, this is at the start of the experiment. By the end of the experiment, still got my beaker. Now it's full of water, not half full of water, as I'm being optimistic. Half full of water. No hydrogen peroxide is left. And oh no, what's happened to the mass? The mass has decreased. Oh, but how can that be? I can't create or destroy matter. No, it just means all this oxygen that's been created has gone off into the air somewhere, and we're not measuring that mass. All the mass of the air isn't pressing down on the scale, because that would just be weird. So because it's gone off, it has what we called escaped into the environment. Okay, so I'll write that down. Escapade to the environment, environs, air if you want, environment. Okay, so in an open system, any gas given off will escape to the environment. Okay, calculate the masses of reactants and products from balanced equations given the mass of one substance. So that is this stuff here. Okay, we've got our balanced equation. Calculate the mass of chlorine needed to make aluminium trichloride. Okay, so we figure out the MR of the molecule, and then we cheat a bit and we do the MR of the substance as a whole. We take account of the big numbers here, just because that's easier for you guys. We put in the data that we've been given, mass divided by the MR, always mass on top, just remember that, which gives us our little ratio here. And then we just multiply the MR of the substance up to get the grams that are needed, and then we check that the total mass is the same on each side. Remember, because that is our conservation of mass stuff there. I know that a few of you were having problems with that. If you can just remember, write down your mass, write down your MR, and do mass divided by MR. That's most of the marks. Okay, so just do your best with it. That's all I'm asking. Okay, we did another example here with titanium, which you guys did. So watch the videos. I'm going to go through it a lot more slowly. And then calculate the concentration of a solution in grams per decimeter cubed. Right, now I am just going to check. They've not given you, there weren't any of the 2008 paper that I have sent. Oh no, there was. And they have written it, if you look at this, instead of writing it nicely, they've written it grams times decimeter to the -3. Okay, it means exactly the same thing, grams per meter cubed. Okay, it's just written like that. You guys are going to be doing this, and I'll be working through it later as well. Yeah, grams per decimeter cubed. And it is as it says, the mass, the grams, divided by the volume, the decimeter cubed. So even if you forget how to do it, you always put the mass on top, so that's easy. And as well, the units of grams per decimeter cubed they tell you what the sum you're doing, grams per decimeter cubed. It tells you the sum. So hopefully that'll be a bit easier. That's it for the foundation paper. I'm going to just do a little bit on the higher paper. Okay, so really, really quickly. Okay, recall that the mole of particles in a substance is defined as the Avogadro constant, which is 6.02 times 10 to the 23, of particles of that substance, of a mass of relative particle mass in grams. So 12 grams of carbon is a mole of carbon. 24 grams of carbon is 2 moles of carbon. 6 grams of carbon is half a mole of carbon. Okay, it is what it is. You understood it when I went through it with you in the class. Okay, calculate the number of moles of a particle in a substance on a given mass of that substance and vice versa. So it's just as I was doing with the carbon. You know, however many grams you've got, divide that by the AR or the MR, and you've got your answer, how many moles you've got. Okay, remember it is mass over Mr. Mole. Mass always goes at the top, which means everything else is just times together. Calculate the number of particles in a substance given the number of moles. Okay, so that's what we've done here. How many molecules in 9 grams of water? Okay, so we've got 9 grams, we've divided it by 18 because that's our MR, so we've done our mass divided by MR, so we've got half a mole, and then you just times that by Avogadro's constant to give you how many molecules you've got. It's not rocket science, it's just moles times Avogadro number gives you the amount of molecules. Explain why in a reaction the mass of the product formed is controlled by the mass of the reactant, which is not in excess. Okay, so I've got a reaction, okay? 1 green reacts with 1 gold to create a new particle, okay? In this reaction, I've got loads more gold than I have green, okay? So the gold is what we call in excess. I've got too much of it. So it's going to react. And I've got another goldy greenie. And then I've got another goldy greenie. I've used up all my greens. Oh no, but I've got all of these goldies left. How could I make this reaction go faster? Could I add more gold? Well, no, because what would be the point? The gold's in excess. If I added, on the other hand, another green, look what I can do. I can, make another one. So the mass of the product formed, this stuff, has been controlled by the reactant not in excess. The green one was not in excess. The gold one was in excess, so the green one wasn't. So that's why it controls the reaction, because once it's used up, the reaction stops. Okay, last one. Deduce the stoichiometry of a reaction from the masses. The stoichiometry, that's a funny word. That just means the big numbers. So balance the equation, basically, of a reaction using the masses of reactants and products. And that's what we did here. Okay, balancing the equations with the moles. And we did mass over Mr. to give you the moles. Divide it by the smallest to get 1 and 2. So you know that have to be, those two numbers have to be 1 and 2. Ideally, they would give you the masses of these as well, so that you could do it completely. But if not, you just balance it as you would do normally. Okay, if there are any questions, please do email me and let me know. What I'm going to do now, though, is go through the answers for the questions that I have set you. Okay, so